So welcome back. We're going to continue talking about corrosion in this next lecture. In the previous lecture, we spent a lot of time talking about the real fundamental mechanisms driving aqueous corrosion, where we know that the oxidation reaction occurs at the anode, which is where the corrosion process occurs. But in order for corrosion to occur, we also need the reduction reaction occurring at the cathode. Now, as engineers in this part, what we're really going to be interested in is how do we avoid corrosion and what are the common corrosion processes that are out there. So this is a little more of the practical application side of corrosion. So as we move forward, we're going to start with our quote of the day as we usually do from Albert Einstein, as like everybody knows who Albert was. And so really to look at problems at a new angle. And I chose this quote particularly because there tends to be a lot of creativity required in how you avoid corrosion. And this goes back to sort of the practical applications of science that we've been talking about in these quotes as we've been going on. But as we get into the lecture, we're going to really concentrate on a couple of things. The first one is passivation. And the idea behind passivation, which is really the formation of a thin oxide film on what we consider to be corrosion-resistant materials. Stainless steel is probably the best example of this type of corrosion-resistant material. And passivation is critical to that. Now, all materials passivate, or all metals, I should say, passivate. But with that, not all of them passivate in the same way. So the formation of this thin oxide film can minimize or at least put off some of the corrosion activities. Now, corrosion occurs in different ways, and we're going to talk a lot more about that. And so when we start talking about that, we're going to see that there are about 8 different forms of corrosion that are important that we run into on a daily basis, and what we really see when we have corrosion type activities. Now, most important for practicing engineers, especially mechanical and industrial engineers, usually designing things, is what affects corrosion and how do you suppress it. And so Callister, once again, I'd say read the chapter, and the problems from the previous sub-lecture that we had will cover your homework assignment. So what is passivation? So some materials tend to lose their chemical reactivity. They become inert under certain environmental conditions. One of the most common one is seawater. Seawater is an extremely corrosive environment. It's a very difficult environment to work in. That's why when we talk about corrosion, we see that the marine industry, the Navy, offshore oil, and gas exploration, they concentrate, they really pay a lot of attention to corrosion. And certain materials form this passive film that we talked about. And it's very thin oxide film. And when we talk about thin, we're talking between 10 and 100 angstroms. It's sometimes what we call a monomolecular film. Now, bulk films are something different. We can grow those through some different processes. One type of bulk film you can even think of as paint. Those are more corrosion mitigation things that you would do, that you would try to suppress corrosion. But most metals will naturally develop this film. And depending on how protective that film is and how rapidly it reforms will tell you something about how corrosion resistant that material is. So a passive film is this thin monomolecular film. It's what is important to remember here. Now, we talked about polarization curves the last time. What we saw was the activation polarization. And so if we were to look at corrosion as that electrochemical problem that we've been talking about, we need to look at density because we know there's electron transfer between the anode and the cathode, and we can drive that by changing the potential or that pressure, very much like you might remember from your physics classes talking about the basics of electricity, Ohm's law, V equals IR. And so in corrosion, we do a lot of the same things where we'll vary the potential and look at what the impact on the current density is. So what we'll try to do is drive the corrosion process. And at these low potentials, in a lot of cases, what we tend to see is we can drive that activation corrosion process. And what we see here is that oxidation reaction leading to corrosion. So under a certain potential, we have that. But if we keep raising the potential, what we tend to see is we'll start to see a significant drop in that current density that goes along with it. And this drop can be looked at as a passive region. With a low current density, thinking back to what corrosion is, do we have electron transfer? No, we don't. And so with that, what we start to see is a increase in the corrosion resistance. And so there's a passive film, and it's an oxide film. It tends to be somewhat insulating. So with that, what we've done is we've changed that polarization that we talked about in the last lecture. And what we have is a passive region. So the way to think about it is corrosion occurs in the active region. I would mark that down here if I were you. Within the passive region, there's no corrosion. And so we want to try to operate, especially with designs in these type of marine environments or corrosive environments, we want to operate in this passive region where that passive film is stable. Now, if we keep upping the potential, what we start to see is we start to see a transpassive region. And that's where the oxide film will start to break down. And when it breaks down, we start to see the more traditional corrosion that we would tend to expect. And this is called a transpassive region. It's just like anything else. If you put enough current through any type of insulator, sooner or later that insulator will break down and it will start to conduct. It just depends on how much potential you can apply to that. So we see that. So active region corrosion, passive region no corrosion is what's important there. And stainless steels, really one of my favorite types of material systems, and one that I'll spend a lot of time when we start talking about steels in upcoming lectures. We're going to spend time talking about stainless steels. They're widely used because of this ability to form this passive film, which is fairly tough, it's fairly adherent, and it allows you to operate in environments with ferrous materials that you wouldn't normally be able to operate in. Now, what makes a stainless steel? There's a certain number, and at least 11% chrome. That's a key number to remember with stainless steels. If you take an iron and you add 11% chrome to it, it's no longer what we look at as a plain carbon steel, but it becomes a stainless steel. Now, the arch in St. Louis is a one that we can look at. If you can go there, you can walk right up to it, touch it, see that it's a welded stainless steel structure, or some other more common components where piping for chemical plants and different places where you might have some seawater and other places. So stainless steels are widely used in that. Now, even in history, going back millennia, we see that there were examples even then of the ability to passivate or produce a passive film. Now, the iron pillar of Delhi has been around, as we see, since 375, 400 AD, or whatever we're looking at is that our nomenclature now. And if we look at it, it's 98% wrought iron. It should have rusted away, shouldn't it? If it's just iron, why is this pillar still basically in the same condition it was, not quite 2000, but about 1800 years ago? So it has a passive film. And so when they processed the wrought iron with this, they ended up with a lot of other types of oxides and phosphorus in the metal. And sort of what happened is during a monsoon season or a dry season, you had this sort of alternate wetting and drying. And what happened was when it became conditions where there was a lot of moisture in the air, a thick, rather passive film formed over the pillar. And so the pillar has been able to withstand that. And part of it was a little luck of the chemistry, but what it was the formation of this passive film. So we see this passive film as being important, and we see some industrial applications, we see some historical applications. Now let's step back and look at how many different types of corrosion there are. And so when we look at metallic corrosion, we have 8. Uniform, galvanic, crevice pitting, intergranular, which means a grain boundary, selective leaching, which we're going to see in copper type alloys, erosion corrosion, and stress corrosion. So let's go over each one. Uniform corrosion. This is one where it's not attractive, as we can see just from these images of lampposts and piers and bridges where they're maybe exposed to some marine environments, or even in the rainwater, having some high level of acidity leads to this general type of corrosion. But it's something that occurs across the entire part. And the oxidation and reduction reactions are occurring randomly over the surface. So if we have this scalar deposit, sometimes we can use that a little bit to our advantage. It acts as almost that passive film that we saw in the iron pillar of Delhi, but it is unattractive, but it's something that's predictable. And as engineers, we're always after things that are predictable and decrease uncertainty. And with that, we can sort of watch how corrosion occurs on these. Say for this bridge section, there's a lot of corrosion on it, but what we can do over time is just measure the thickness and measure that loss rate for that corrosion penetration rate that we talked about, where we have a certain loss in mils per year, hopefully. And with that, we can predict when these failures are going to occur if we really are interested in what's happening with that structure. We could actually run the finite element analyses as the material becomes thinner and thinner and determine when we're going to have potential for some type of failure and make repairs before that happens. So uniform corrosion, even though it's unattractive, is really something that's predictable, something we probably prefer to have. Galvanic corrosion, on the other hand, this occurs when you have two different metals in contact with each other. And in this case, what you tend to have is sort of a less noble aluminum guard. They call it guardrail here. I think the appropriate term these days is guide rail, because it doesn't really guard you against anything, and steel. And with the steel, if we remember our galvanic series, we know that aluminum is lower on it. So the less noble will experience corrosion while the inner metal will somewhat remain protected. Now, even though it looks bad in this case with the guide rail failing in the way it is, if we really think about how we want to do this, we'd rather have a steel or the type of fastener be the material that is more noble or more cathodic. And with that, we want the corrosion to occur over a larger area. In this case, it became somewhat localized, but with the larger area, the corrosion won't take as long, and failure is something that we can see happening. Because if the fastener is failing, that could be a little bit more of a problem. Now, so we have uniform, galvanic. The next one we want to really talk about is crevice corrosion. Crevice corrosion is a little bit more insidious. This is not something that we can see happening. And so in the schematic here that I've taken from the Callister textbook, what we can see is a lap joint around a rivet. Now, if we go back to lesson 0, or the introductory lesson of the course, I showed a fatigue failure in a couple aircraft. Now, those aircraft are riveted skins. And so with the Aloha Airlines flight, you had some corrosion issues, and probably in all likelihood a crevice corrosion issue. And what makes crevice corrosion a little different from galvanic and uniform corrosion is that crevice corrosion is more localized. And what it is, it occurs between this gap, or this crevice between two metals that are held in almost intimate contact. And with that, as you start thinking about capillary forces, you can draw in a small amount of liquid in there, but that liquid becomes trapped. And so what happens with that electrolyte, or that liquid gets in there, you start to get some concentration differences. And you can deplete the oxygen, but that electrolyte in there becomes extremely rich in H+, which means our pH is going way down. And with that, what we're going to do is we're going to accelerate the corrosion process within that. Now, they can develop these high concentrations of H+ and even Cl or chlorine ions. And chlorine ions are well known for enhancing corrosion resistance in certain materials, particularly ferrous materials. And so with that, we start getting everything happening. We get our electrochemical cell happening in a very concentrated area. And what can happen, washers are a great example. You have a crevice, you'll see these type of very damage that you don't see coming. Incomplete weld penetration is another one. I like this example primarily as a welder, but we do a lot of tube welding. There's far more tube welding. There's miles and miles of tube welding in any type of energy plant or anything like that now, or chemical plant, or any place where you have fluid flowing through tubes and pipes. And so with this weld, if we don't control the penetration of that weld, what we can get is a very small area of that weld where we have a gap. And as with anything else, we have flowing liquid through there. That small gap can lead to capillary forces. It can wick some of the material, some of the electrolyte, or that fluid that we're flowing through the pipe into that incomplete weld. And it leads to this type of crevice corrosion, because we created a crevice by not having complete penetration of the weld. And so with that, we start to see these types of failures occurring where we see significant corrosion. Now, crevice corrosion can be accelerated far greater than any of the other localized corrosions like pitting.